So good evening all. So today we will see problem solving session 7 on the topic leachings. So here is a brief recap. Basic concept of leaching, then classification of leachings, the rate of leachings, then solid liquid extraction, then leaching a single stage operation, and leaching multi-stage operation, then supercritical fluid extraction and equipment for the leaching. The question was leaching is a process in which general leaching is a process to separate the soluble separation of the soluble solute with the help of means separation of the solute from the solid with the help of the solvent, that is called the leachings, or in another word we can say solid liquid extractions. For example, like tea, uh, tea powders, like so here is a solute present that helps to make a tea, right? So here we use the water as a solvent, right? So with the help of the heatings, so it increase the solubility of the solute in the solvent, right? So this is called the leaching process. So now we can check the options. Solid is a dissolved in a liquid solvent. The liquid is evaporated from the solid. Solid and liquid mix into form suspension. Liquid is adds up on the solids. So here the solid is dissolved in the liquid solvent to separate out the solute. Moving to the question number 2, which of the following is not a type of leachings? The option given, based on the option we have to select which is not a type of the leaching. In situ leachings, this is also the type of the leaching, heap leachings, then chemical leachings also. So ultrasonic leaching is not a type of the leachings. So option C is a correct one. Moving to the question number 3, the rate of leaching primarily depend on. The option given temperature and pressure, so it also depends the means it depends the rate of leaching, because if increase the temperature, increase the solubility of solute in the solvent, right? And also it helps for the diffusivity of solute from solid into the solvent. And also pressure also important when the super uh, superfluid extractions at a supercritical conditions. So this also impact. And surface area of solid particles, yeah, the small size of the solid that provide the more surface area for the contact between the solute and the solvent. So it increase the rate of the leachings. Means a small particle size of the solid. And also agitation of the mixture, because it helps to contact of solute and the solvent. And also agitation of the mixtures, helps to inhibit the saturation of the solvent on a solid surface. So all the factors are means important to decide the rate of the leachings. So option D is correct. Question 4, which of the following process can accelerate the leachings? So here drying. So drying is a phenomena to remove the moisture from the solid surface. Right. So this is not. So heating and crushing and grinding are both uh, can accelerate the leachings, because heatings improve the solubility of solute in the solvent, and also improve the diffusivity. And say crushing and grinding also, small particle size provide the more surface area, so that solute and means more interaction between the solute and a solvent. So A and C can accelerate the leaching process, heating and crushing and grinding. Moving to the question number 5. The solar extraction of oil from the seed, which of the following forms of the solid gives the highest rate of the extraction? Okay, here is a different type of solid use. So, so this type of solid gives the highest rate of the extraction. So whole solid. So here is a less surface area provided to contact for interaction of solid and solvents. Broken surface. This is also possible to for a high rate of the extraction. You can see the flakes of the seed. This is a very small size of the seed. So it provide the most for the extraction of the oil from the seed. But based on that, the flakes of seed can provide the highest rate of extraction compared to the broken seed. Coming to the question number 6, solid liquid extraction is solid between solid and solvent depend on. Here is the study. Solid agent and solid, right? So distribution of solute between the solid and solvent depend on the temperature, not pressure only, temperature only, pressure only. So the concentration and temperature and agitation rate. So option is here is correct. Thus temperature improves the solubility of solvent in solvent, and concentration is the means transmit diffusivity. Like, means concentration means it was not driving force, concentration driving force for the transfer of the solute to the solvent. So concentration temperature means distribution of solute between the solid and solvent depend on the concentration and the temperature. Into the question number 7, in a single stage leaching operation, the solute is. So completely remove one inner step. So this is not possible. Partially removed and the process is repeated. So it can possible only dissolve, not separated. Generally, leaching is a process to separation of the solute from the solid with the help of the solvent. To convert into the gas phase, this is not possible. So the option B is the correct. So moving to the question number 8, the multi-stage leaching is typically preferred over the single-stage leaching because it's a simple answer. So it achieves the higher solute recovery. In a single, moving to the question number 9, if the solution retained in the solid has the same composition as that of a solid free, if the solution retained in the solid has means same same composition as that of the solid free overflow, then the tie line. So means solute present in the underflow, which is equal to the solute in the overflow. Then the tie line on the right triangular plots. So here is a right triangular plot, right? So A 100%. This is A inert. B solvent 100%, right? And C the solute 100%. Okay. So this is a overflow. This is a underflow, right? Like here is a LLE process. Feed solvent streams VL. We do not have the overflow. So means after separate the solute from the solid, and here is a sludge. Means sludge means L means remaining solution, right? So here is a tie line. Means here is the same means at after attain the equilibrium. So it pass through the vertex of the solid, right? Right. So say option C is correct. So pass through the vertex representing the 100% solid. This is a overflow. This is a underflow. So for examples, when the tea powders used to make a tea, right? So here is a solute presents, which are partial miscible with a solid. So when we use waters, right? So it form a tea, right? So means some solute extract with the help of the waters. That's called the tea. That is called the overflow. Now, whatever the amount remaining in the solid, that's called the underflow. Moving to the question number 10, if the solute concentration on a solid free basis in overflow and underflow are equal. Okay, here mentioned that the solid free basis. The tie line are, here is a Z is a mass ratio, right? XC by C, right? So this is a underflow. This is a composition of the overflow. So this data get from the X-ray by experiment. So we have to change the different concentration. So after attend the equilibrium, then we measure the concentration of the both phase, means underflow and the overflow. Based on that, we'll get the data, and then we can draw this graph. So after the attend equilibriums, then we can draw the tie lines. So in a solid free basis, so it's the tie line are a vertical. Moving to the question number 11. In a counter current leaching battery, the overflow from the stage are essentially solid free. What is the slope of YCZ plot? Here is the plot Z versus YC, right? YC, XC. So here is the overflow from the stage are essentially the solid free. So this is the YC denote for the overflow concentration, and XC denote for the solid concentration in a underflow, right? So here is the what is the slope of the YCZ plots? So like this is, so such straight line goes through the x-axis. So we have to calculate the slope of this line, right? The slope is y2 minus y1 divided by x2 minus x1, right? So here, so y here is a 0, y2, so suppose this point, so 0 is particular like anything like, for example, 5 or 4, if the difference like 5, it's a 0. So moving to the question number 12. Which of the following fluid is commonly used as supercritical fluid extractions? So generally the amongst most commonly used is carbon dioxide uh, used in the supercritical food extractions. So because it's a relatively low critical temperature and pressures compared to the other ones. So the critical temperature carbon dioxide 31 degrees Celsius and 73 bar. Now this CO2 is a more compatible for the extraction of the solid from the solid. Now move to the question number 13. Which of the following equipment is commonly used for the leachings? So distillation column not used here. Rotary clean used for the like grinding. This is not. Spray towers in the gas absorption. This is not. Agitated tanks used commonly in the leaching. So proper mixing up means proper mixing up solid and the solvent, so that solute can transfer it to the solvent, and also it helps the mixing, helps to remove the means inhibit the saturation of the solvent on the solid surface. Now moving to the question number 14. If the solvent viscosity is low and temperature of the solvent is high, then the leaching rate decrease. Here is the solvent viscosity is low and temperature of the solvent is high, then the leaching rate decrease. So you have to decide is this statement true or false. So generally solvent viscosity is low and temperature is high. So it temperature of solvent is high, which improve the solubility of solute in the solvent, and low viscosity helps for the diffusivity of the solute to the solvent. Right. So here so this statement for increasing the rate of the leachings. So this statement is a false. Now temperature of the solvent is low. So this is also false, because for the for improving means improving the rate of the leachings of solute to the solvents. So temperature of solvent should be high. Question number 16. Leaching equilibrium is the same as the thermodynamic equilibrium in case of the other mass transfer operations. So this so in this in a leaching process, so at equilibriums, so like solute in a overflow equal to solute solute in overflow solute in a underflow, right? So this is this happens at a equilibrium in a leaching process, and like for a liquid extraction, right? So whatever the like yep solvent E rapid, right? So here the whatever the uh, distribution means whatever the solvent capacity to extract the solute, right? So that is called the extraction efficiency, but the concentration of the solute in the extractant activate is not same. But in a leachings, the solute in the overflow equal to the solute the underflow, right? So this leaching equilibrium is analogous to the thermodynamic equilibrium, right? Because thermodynamic equilibrium is temperature pressure constant. That's called the thermodynamic equilibrium. So this statement is true. Moving to the question number 17. A solid material contains 10% of solute by the weight. A leaching process is leaching process is used, and 90% of solute is dissolved in a solvent. If 100 kg of solid material is processed, how much the solute is? Here is a 100 kg solid materials. So in that material is 10% of the solute by the weight, right? So in a leaching process, the 90% of solute is dissolved in a solvent, right? So initial solute in a solid. %10 of 100, right? So 10 kg, right? Now 90% of solute is recovered. So solute recovered. 90% of 10, right? So 9 kg. So now, 9 kg of solute is recovered. Question number 18. A leaching operation is performed at a two different temperature at 25 degrees Celsius. Leaching rate is 0.5 kg per hour, and at 50 degrees Celsius, it increased the 1.2 hours. By what factor has the leaching rate increased due to the temperature change? Right? To calculate the factors, so leaching rate increase 1.2 divided by 0.5. That's the 2.4. So here just to ask the what factor has the leaching rate increase due to the temperature change. That is the 2.4. Question 19. In a solid liquid extraction process, 10 kg of solid contains 3 kg of solute. The distribution coefficient K for the solute between the solid and the solvent is 0.5. So mass of solute in a solid divided by mass of solute in a solute. Calculate the mass of solute in the solvent if the system reach equilibrium. Right. So here is a distribution coefficient value given 0.5, and distribution coefficient is the mass of solute in a solid divided by mass of solute in a solvent, right? K is equal to, that is a 0.5 mass solute in a solid divided by mass of solute in a solvent, right? So initially at a feed 3 kg of solute present, right? Now we don't know the quantity of the solvent. So let a mass of solute in a solvent be S. Like this is a yes, right? This is the mass of solute in the solvent, right? So 0.5, right? So in a solid, 3 minus S divided by S, right? So yes, the mass of the solute, in a solvent is a 2 kg. Moving to the question number 20. In a multi-stage leaching process, each stage remove the 70% of the solute from the solid if Initial mass of solute in the solid is 10 kg. Calculate the mass of the solute remaining after the two stage. So here the multi-stage leaching process. So each stage remove the 70% of the solute from the solid. And if the initial mass of the solute in the solid is 10 kg, so you have to calculate the mass of solute remaining after the two stage in the solid. So after the first in the first stage, right, the solute removed is 70%, right? So 70 of here is a 10 kg, it's a 7 kg, right? So solute remaining now 10 minus 7 is a 3 kg, right? So this is the first stage. In the second stage, solute removed 70% of 3, right? It's a 2.1. And solute remaining in underflow. So 3 minus 2.1, that's a 0.9. So here is a mass of the solute remaining after the two stage in underflow. Now question number 21. 1 kilogram of sludge containing containing 0.5 kg of CaCO3 and 0.1 1.5 kg NOH. This is a solute. This is a inert, and 0.35 kg water is a mix. This is solvent. The solvent present in also feed mixed with the 1 kg of the water. The suspension is allowed to settle, and overflow and underflow are separated. Right? This is feed. This is a solvent. This is the overflow. So overflow denoted by V and underflow denoted by the L. The underflow has a 0.3 kg solution retained per kg of inert. So here 0.3 kg solution per kg inert, right? So calculate the amount and concentration of solute in the overflow if it is a free from the solid. So we have to calculate the amount of the solute and concentrations. right? So here you have to here is the one assumptions. The NOH, this is a solid. NOH concentrations in overflow and underflow are the equal. NaOH concentration in the overflow and underflow are equal, right? Now total solute is equal to 0.15 kg, and total solvent denoted by total solvent 1 plus 0.15 0.35, that's the 1.35 kg, right? Now here mentioned that 0.3 kg solutions retained per kg of the inert, right? So mass of the solution retained in underflow, right, is a 0.3 into kg inert. Here is a 0.5 inert, right? That's a 0.15 kg. So mass of the solution in the underflow, that's the L, is a 0.15 kg. Now mass of overflow, that is V, there is a 1, then 0.35, this waters are present in the feed, and 0.15, right? Minus this one 0.15, that is 1.35 kg. This is the mass of the overflow. Now solute concentration in a overflow, it's 0.15 divided by this is mass of overflow 1.35, that's a 0.11. So this is the concentration of solute in the overflow, right? Now mass of NaOH extracted, mass of solute means NaOH extracted 1.35 into 0.11. So 0.149. One four, right? So you calculated the amount of the solute in the overflow and also concentration calculated here. So if you we can also calculate the fractional recovery of the solute from the feed. So here is a 0.149 divided by 0.15, right? Means extraction, you can say fraction recovery of solute. Fraction recovery of the solute divided by around almost 99%. Solute recovery. So question number 22. Solid bit containing 22% of the solute, 3% waters, and 75% inert to be leached at a rate of 1 ton per hour. Of 1 ton per hour with the water in a counter current leaching cascade. Okay, here water is solvent. The strong leachate leaving the unit should have a 16% of the solute in it. So desire recovery of the solute in the feed is the 99%. Okay, 90%, 99% of the solute recovery. The overflow does not have any intent inert in it, and the amount of solution retained in the sludge is 0.45 kg per kg inert. Okay, inert, this is underflow, kg of solution per kg. So analytically determine the number of the stage required for the separations. Right. So feed is a 1000 kg centralized, and the mass of inert it's a 750 kg, right? And then S2 water in a feed, mass of the water in a feed 220, sorry, 30 kg, and solute, mass of solute in a feed 220 kg per hour, right? Right. Feed solvent rate V and L. So here is a 99% recovery of the solute. Now here the strong leachate leaving the unit should have 16%. So 16. So it's a Yn is equal to 0.16. And in underflow, the retained the amount of solutions is 0.45 kg solution per kg inert. Correct. So here is not a solute present in the overflow. So solution leaving with this inert, like that's a L. This is a solute free. Dash denote the solute free. L dash is equal to 750 into 0.45, right? So kg inert get cancels. So that's a 337.5 kg per hour. So this is the solution of living with the inert. That's the L dash. Now mass of the solute leaving the in a underflow. So 99% the recovery means is in the solute present in the underflow. It's for 1%. So I can write down XCL 220 initially present 220 into 0.01. That's 2.2 kg per hour. Now solute concentration in the underflow. Sorry, here mass of solute in the underflow. Now solute concentration X C, right, 2.2 divided by L, weight of mass of underflow 337.5. This is a 0.00652. So mass of fraction on a solid bed, that's considered X1, right? Near the YN, here is a strong digit leaving the unit should have the 16%. Now you have to make a solute balance. So solute in a underflow plus solute in a overflow, that's a V, right, equal to the feed. So here is a the solute in a feed is a 220, right, 220. And solute in a underflow 2.2. So here before going to this one, so here MW denote for the water entering, including the feed and this ones. So MW. So solute in a V is mw minus 337 minus 5 minus 2.2. So this is a water. So 1 minute. So here it's a in underflow. So 2.2 kg per hour of the solute. So now water present in this underflow. 337.5 minus 2.2. So 339 kg per hour, right? Water leaving the sludge. Now we have to come to the solute balance. So solute in the underflow plus solute in the overflow equal to the solute in a feed, right? So to solute in underflow 2.2. So in the overflow mw minus 335 3, right, into 0.16 1 minus 1 minus 0.16, so 0.84, right? So this is the mass of solute in the overflow. So equal to the feed 220, right? So here is a mass of water entering. MW is a water entering, including that present in the feed, right? So here after calculating, so AMW is a 1478.75 kg per hour. So water entering is a 30 kg per hour, right? So now water leaving in the overflow in the overflow. MW minus 335, this one's 0.3, right? 1 1 40 kg per hour, right? Now water entering as a solvent, that is denoted the V, sorry, V not dash into 1478 minus 75 minus 30 initially present 30 kg per hour. So 1448.75, right? Now to calculate the number of stage, is a formula n is equal to log 1 plus r minus 1 into xn minus x naught x1 minus x0 divided by log r, right? So here is a r equal to v naught dash divided by l dash, right? So here is a v naught dash and l dash we calculated. 1448, right? Here is 75 divided by 337.5. It is a 4.293, right? Now xn yn, right, is 0.16, right? Y0 equal to 0 x0, right? X1 is a 0.0652, the calculated. It's a solute concentration in the underflow, right? 0.00652. So all the value calculated. Now put a value in the equation, in this equation. X in 0.16, x naught is equal to 0, and x1 is a 0.00652. So the n value is 3. So required number of stages is a number of stages are required 3 to attain the 16% of the 16% of solute, means to recover the 99% of the solute. Recovery of the solute is 99%, so required the 3 stages. So I cover all the question based on the leaching chapters. So thank you all. So we will meet on next Friday on next chapters.